All right. Right, so I got a very good question during the break to ask, okay, so I search both branch, right? We keep searching. So the lady was asking, is the computer doing the searching parallelly or they do search one by one? So I haven't thought about how the computer programs so for days. It may be relevant to computer lecture, but I think it's a very interesting question. If anyone knows more about the computer hardware or how they compute this, is it parallel or they keep searching each branch? To me, it seems that it should be computing several nodes at the same time. It will be most efficient, but I think it's very, very interesting if you want to think about how computers think really in the computing. That really gives you more potential to develop the most efficient algorithm to go further. Right, but the key thing here is that if you come back to see this figure, it really gives you the whole bunch process, right? If you go to your relaxed problem, then you add your constraints to be easier to search about x1 larger or equal than the 2 or smaller or equal to 1, then you are able to find the optimal points at each of the newly defined zone. Then it's possible that we got some, if one zone, not only we stop, we only stop if one redefined branch is infeasible. We won't go further with that because we keep adding constraints. At one point, it might become infeasible. So we will stop at that infeasible point. But it's also possible because we keep adding different constraints. We might get some new solutions, even new integer solutions at both directions. Then you compare those solutions to see which gives us the optimal final value. So this keep giving the branch. For simpler problems, it will stop after several layers, so it's quite efficient to find optimal solution. Because you always keep do the relaxation first, then give you the lower bound, and then you just keep to search for all the feasible solutions. So the feasible solutions will then be compared to find you the minimal, compare with all these minimal your solutions and find the optimal one among the feasible solutions. So like in the end, we compare, when we cannot finish, cannot continue, we will get several feasible integer solutions and compare those to give you the optimal among those set of feasible solutions. So this is the algorithm. So this is an example, so it's simple. Again, only 2D, we can easily see it, x1 and x2. I want to maximize, so it's again giving you maximization, so you get to reverse your math, because now I want to get maximal value, then the relaxation becomes the positive action. I want to maximize my, here, some of the profit, for example. So if I linearize it, I will get at least a solution that gives me the lower bound or upper bound. Upper bound or lower bound. So for optimize, like now we want to maximize some solution. And for example, I have my, initially if I say my x1 are integers, non-negative integers, but then I first relax my program to say x1 and x2 are just non-negative variable, so I don't say they are integers, and then I solve for the whole program and get the solution to this LP problem to be here at this point, because it's not integer from the first round of solve here. So can you tell this is this optimal solution x1 plus x2? Is this a upper bound or this is a lower bound? Upper, right? Because it's relaxed. I want to maximize and then I further relax it. So this optimal solution has to be either equal or smaller than this when adding the integer constraint. So this kind of gives me a peak already here. So it's the first step, so the LP. And next one, I then start to go from my upper bound to continue to do my branch to build up the tree. Okay, so instead of the non-negative constraint, I then decide, because the first one I got my x1 equals 1.5, right? Then I divide the branch, one x1 smaller or equal than 1, and the other larger or equal than 2. So this is my first branch based on x1. Okay, so this is the computing process. I then solve this LP problem, and again find my solution. So here I got my x1 already at solution of 1 and 7 over 3. Right, because my x1 is smaller equal to 1, so it's when x1 equals to 1, it means this x1 really is at the boundary. So it becomes an active constraint. I find my solution x1 is integer here. But still, we just solve for this LP using the LP algorithm and got my solution. And my z value, my object function is 10 over 3. All right, and same for this, I solve for the other branch and got my feasible solution. Again, x1 is at the boundary, so x1 is 2, and x2 is 23 over 9, which is larger. Oh, sorry, this z is 41 over 9, right? So this is 3.3, and this is 4.6, 4.5. So this gives us a larger value because it's maximization. So I continue with this branch because this branch gives a larger value. So this is why we don't really need to compare in the end the parallel processing, because this branch already gives me other value than this. So I know I will continue with this most promising branch. The other one, if you keep adding more constraints, it won't become better than this one. So I continue to add more branches to this one. To add the branch on x2. So now x1 is cut the branch already, but x2, based on the previous value, x2 is 23 over 9. Right, so then I use the value 2 and 3 on each side to add another two constraints of 2 and larger than 3 to be the new branch based on x2. And again, solve this LP. So here is no feasible solution because you really add too many constraints and already no feasible region to give you a solution. Therefore, this branch is cut instead. Then I come to this and again get one optimal point and the solution. So I go with this one. I got the solution here, solved from the original problem, still the LP problem, and still the solution is not integer. So I have to continue. Although I know this is a good direction, but still not integer. Okay, so at this point, it will then be a rounding step because it's already at the point of the of only this branch is active, but because it's simple example only x1, x2, so it will do another round of the calculation to give you the break the branch at x1 and search for the optimal results. So how does this final solution look like? So in this case, actually, the MILP gives you two feasible solutions that returns the same optimal value, right? So at the final step, when you cut the first tree, the second one you keep x2 smaller or equal than 2, and continue to find it, either to make x1 either to equals 2 or to make it larger or equal than 3 to cut the branch. So here it's only show one way to cut the tree. You can also cut the tree if you can have different, because here final calculation you find a way to define x1 and x2. x1 is 2 and x1 larger or equal than 3, and you find both optimal solutions. Right, so this is iteratively show you how you go along it to cut each variable. Once you find that if it's non-integer, go around this non-integer variable to add in two different constraints and make a new LP program to solve for the solution until you reach the integer solutions. So it might be two equally good integer solutions in this case. But this is in real process, you don't have to calculate, you don't have to build the tree yourself, right? Computer is there to help you build the way. But the searching process is what we understand how it builds the branch and the bound to finally find the solution. Okay. So this is the algorithm review. If we say I will do the B and the B, its overall algorithm is always first to solve LP problem, use a relaxation problem to find the lower bound if it's a minimization, minimize cost for the current branch. If the solution exceeds the upper bound, then this branch if this solution does not exist, then this branch is terminated. But if this solution is integer, so our goal is to find all the integer solutions of this that has an optimal value, right? You got the lower bound for the problem, then you keep searching for the different branches. If you find the solution of integer, then you define this as a new upper bound of the cost function. Because it's you find feasible solutions to replace there, then you continue to calculate the other branch until you find a new feasible solution and replace this current integer solution that has better optimal value. So this creates every time to add two different branch problems by adding constraints to the original one. And just repeat until there is no branch, you got the final solution. So this is the whole way how it calculates using the BNB algorithm. Okay. So with this in mind, that's for general, right? That's for general algorithm. Then we also, most time we formulate the problem as a binary variable. So it's probably easier if we see binary is only 0 or 1. Even in numeration, we can write down all the possible combination, although it's very computationally expensive. But then if I can use the branch and bound method for my binary, I no longer need to use the inequality constraint. I can directly cut the tree by 0 or 1. So that's a special case we showed here. If you start with any problem that only considers any MIP problem, but only binary variables, not the other integer variables, special case, then we still do the same relaxation process to get the LP. Right, you got LP and you got objective function, then start to search for each variable to cut the branch based on its 0 or its 1. So here is coming X, is a variable. You cut from 0, cut from 1, and then calculate the objective function. Right, so it's don't have to really, it's kind of enumeration because you already say 0 to 1 for an initial tree. But when you continue to build up the tree, you will be able to find, here if I want to find my minimization problem to get my minimal value, so I relax it first. So this is my lower bound. So I got my lower bound here and continue to different branch. And I already realized here, my objective function is larger than this tree, but I still keep, I won't stop here because it's still feasible. But of course, it's because it's add more constraints, this relaxation, it already see a larger objective function, right? So you got the objective function value. This will be your tree at the second level, but you continue to search to find the to get the final Y2 to find the value and choose the optimal one. So this case seems like an enumeration, but in the real algorithm, it will cut some branches. Either it's infeasible, or if this branch is less optimal than the other branch, it will only go with the most promising branch, but not the other less optimal branch. So this way, we don't have to list all the options and compute. We just find, still like the searching algorithm, you find the most promising direction to go. But here, this direction is clearly defined by the integer e. Right? So that is the algorithm, the core. You don't have to know how step by step you calculate. So maybe only chance in class you calculate by hand. But in computer, every time, it will do this searching process. Not enumeration, but still do some to find the optimal solution. Right? So this is another more deeper tree. Right? Where we see for this specified minimization problem with y1 to y4. So it's 4 decision variables, and I have a set of 4 inequality constraints. So it seems quite complex. And I have y1 to y4, 0 to 1. So think about the question, if I have 4 binary variables, how many combinations will I have if I do a exhaustive enumeration? Okay, again, that's a lot, not a lot for 4, but still, can we use some branch and bound method, B and B method to find the solution? Right, so this is a way, if you go with y4, for example, relax it first and get optimal solution. Already y1 equals 0 from LP, so it's good. Already this y1 meets my binary requirement. Then if I choose another one, if I choose y4 here to continue search, my first branch, y4 equals 0, it will be invisible from this branch. Just add y4 equals 0 to the original problem, it's invisible. So I directly cut the whole branch. I just continue with the y1 equals 1, and then get the second node. And then here I can choose another variable. Of course, how you choose y4 or y2, you can design a new criteria to say, okay, if it's closer to 1 or closer to 0, choose this. So this is part of your choice, which variable you choose to cut the branch. It may cause different effects. It's also one part of the algorithm. Here we just show you further, we choose y2, and still this is 1z, I got the solution, but then this is already integer solution. So I stop here. This tree already gives me 1 integer solution, but I further process here to get this set solution. y3 is still not integer, so I break y3 to 0 and 1. And finally find this is invisible, and this is a final solution. And then compare this, and I got this is optimal. So it's, in the end, it's a comparison to find the optimal solution. This is 0 and 1. So binaries are easier because we just add the equality constraint to solve the problem. So it's just like partition this MILP to a sequential linear programming subproblem. So you can regard this as a SLP, we call sequential linear programs. Instead of solving a mixed integer, you then just solve linear programming. Okay. So it gives you each bounds, continue to find the optimal solution in the end. Right, so this is a B and B method. It's quite powerful in solving many problems and has been the most commonly used problem. But it's also some additional version of how we can further solve integer programming. So we won't directly tell you the details, but it still just give you a sense. It's some new methods. We can call it cutting planes. So it's kind of a lot of new ideas. It's quite creative to think about those algorithms. So these ideas of cutting planes comes from adding additional constraints to LP to improve the tightness of relaxation. So instead of directly remove all the integer variables, the data relaxation is too relaxed. So you want to add additional constraints to improve it. But how do you add those constraints is another decision. You need to get some methods to add. Just the goal is to add more to avoid this over relaxation, and then you can combine the constraints to keep solving and eliminate the non-integer solutions. So you know that you still some relaxation, but now it's not you cut it based on each variable, because before we cut the branch by some boundary, right? So if we visualize it, it's always to cut of below or larger, so it's always some boundaries for the decision variables. So it's kind of you think about adding some straight lines as boundaries. But now instead of adding that kind of the branch, they don't want to cut straight. They cut in some weird format. But this format needs some more specific calculation. But in this way, they can cut, this is cutting plane, add this cut, add the new constraint, and then find continue to solve the LP problem, find the solution, and try to reach the final integer solution. So this is the concept, but when you really operate it, it's quite some different strategy. You even need to define how do you add your cutting plane. So we won't tell the details here, but you know the basic idea for integer is always relaxation. But how to do this relaxation is different algorithm. You can directly cut it by just cut it by some boundary of the variables, or you can add some cutting planes to make it more efficient to solve. So this is also not a very mature, like people still develop more efficient algorithm to say, if I define my cutting plane function in this way, my algorithm will improve. Because you can really cut in any way, right? So you can continue to cut, but you need to guarantee it increase the performance. Normally when we develop new algorithm, it's very interesting. You can try to explain, but sometimes you cannot prove. You just try to compete the others. You compete your new algorithm with the market-ready, commonly used, like 16 simplex, spiral, the 10 algorithms there, and you see my algorithm is more efficient. It solves the problem 2 seconds faster, or even 2 minutes faster for a very complex problem. So then your algorithm will win. So that's a way now how people say I develop a new nice algorithm, or you can even earn a lot of profits. You can sell your algorithm to games, to MATLAB, and earn from it. So that's a way how algorithms are developed. Because it's also a new kind of integer programming is not well developed. Still a lot of new directions there if you want to do operation research, optimization, mathematical research there. Okay? So that is the modeling algorithm part. I just stop here. We just need to know the basic ideas is enough. But the models, I think, how do you model one MILP as we initially reviewed 3 examples? That's very interesting. We should understand more and try to use that in your projects or in your future work to see how the MILP can help your decision making. Right, so here, still again, the example we just reviewed. If you want to decide how to produce a product, a good, and when to produce, like the time, and how much to produce in order to meet a demand for cars and minimize cost. So this is the most common type of the operation problem, especially production plan, manufacturing optimization. Right? And we just say the cost will be the fixed cost of production in any producing period. Well, this variable cost, or operating cost here, or production cost, is proportional to the amount of goods produced. So still remember the initial reactor problem? We have your x as a feedstock, y variable as a decision variable to say yes or no. So my fixed cost will be decided by if I build this line, yes or no. Well, my production cost will then be relevant, proportional to the production amount, like the feedstock amount, x. And also in most cases, we need to consider the storage cost. So that's a cost if you produce something, that's a cost of inventory. Right? If you overproduce to meet the demand, or this over surplus has to be stored in a certain way. So in product, it's inventory cost, and then if in energy, it's energy storage. So this storage cost is very important when you form your problem. It's normally it's not neglected. If you just say, I want to make my production larger or equal than my demand, but it's larger if it's not an active constraint. If it's real larger than the demand, then you have this surplus part. This surplus part needs the storage. So it's one term in your optimization that is to consider what does this number mean. Well, if you really do this, it will be some surplus product. Okay? So then the constraint for this, okay, I must meet the fixed demand. So it can be demand vector, because like here we consider time-dependent operation, or this time period. And here the time period you can consider as a continuous, as a whole continuous time. But most time, this time will also be some discrete variable. You can consider it's hourly, or it's every day. So this will be another integer here for the time, or you can just see a fixed time horizon. Okay. And if you should also consider some initial conditions. Like if you initially have no initial stock, then you start with 0. So your total production will also just be summed up together and meet the demand. Or if you have some initial stock to add that term, and you have your upper bound for the maximum number of goods that can be produced per period, kind of the production capacity. So if we have such problem, as we just discussed, this is a MLP format we write here to give you a sense. It's a very general production optimization. So if you have read through this, so here they use a modeling way to indicate. Sometimes when we write some models, papers, we like to define the symbols instead of the simple X or Y. We like to write in a more meaningful symbol so that it represents something. So if you look at this kind of the optimization MRLP formulation, then you might be able to solve, right? Have a look at this if it corresponds to all the explanation. And think about which variables are integer variables in this problem. Because if you want to use computer to program, you need to indicate this is integer. But in this case, which are my integer variables? So here you have time t, and you can indicate your t as your preferred time scale of daily operation. And with this time t, you will be able to describe kind of in a dynamic way, although it's still discrete time. but it's then able to link the current time to the previous time step. Because the storage is always the linkage. It's related to the previous state coming to the current state. So right, which are the integer variables? Clear? Is production made or production on or stop? Production made continues our integer or binary. So again, link this back to the fixed cost and variable cost we studied, right? So this production will more be the real link to the product. So we should define, of course it can be integer if my product is, I have to be 1 unit or 2 units, but it also can be continuous if it can be 1.5 kg, for example, if it's by weight, right? So it's really based on how you model the problem. That's right, you were thinking and say it can be integer or can be continuous, but really based on what your products are. If you can produce this in continuous weight, then this can be your continuous variable. If you have to produce this by units, I can only make 1 chair, but I cannot make 1.5 chair, then this product made will also be integer. But this is not binary, right? The production will be multiplied by your production cost. Well, this production on very straightforward. It tells you it's on or off. Why do I use the production on? It actually means if I make this production or not. So this must be a binary variable here, because it's multiplied by the fixed cost. So if it's production on, I will have this fixed cost. If it's not, if it's off, this cost is 0. Right. So again, recall the magic constraint we initially have, the x minus 15y smaller or equal to 0. That constraint helps a lot to define if this production is on, I can have this maximum capacity. If this production is off, my production amount must be 0. Okay, and again, the storage is also the same term, same unit as the production. Here, because we have the time, we define the t. So if you model it, you can model to define the initial value. Because initial value you have to give it. It cannot calculate the initial value. The other from t equals. Why do we model in this way? Because you know, right? For whenever you have storage, you know your current production plus your storage will be meeting the demand and the surplus of the storage. So this is the relationship, the mass balance, previous storage state plus the newly produced product equals the demand plus the remaining storage. But if you just write this one, you will get the code return program will say invisible, because this will search from t equals time, initial time, right? If it's search, in some programs it search from 0, in some it starts with 1. So we pay attention to that as well. In GAMS, then it starts from t equals 1. And then it will automatically calculate t equals 1, t minus 1 will go to stock 0. So you say, oh, invisible, because I don't know stock 0. That's how I must start with stock 1. I define this stock 1 initial condition 0. Then when I calculate this, I can start from the time 1 to use this initial condition to calculate move to time equals 2 relating to the initial condition. So it's also the modeling skills. If you got invisible solution, don't be frustrated. It may just be caused by you define your time wrong. It will link to an initial condition and you cannot find it. So it's a common mistake here. Right. Also define program that if you use if you don't define, it might start the time with 0. So you also pay attention that the initial condition means 0 or 1. So define program to define this in starting point. Okay. and then you have your constraints. This is a nice constraint that you have your binary variable multiplied by your maximum production. Right? This is a given parameter. I tell you the maximum is 15, but it's not always this constraint. It's only when I have this production on, this constraint holds. If production is off, this product made will just be 0. This is the whole problem formulation for this example. To understand this example, we can go further to use the 0 and 1 to think about some logic problems. Because the 0, 1, they call logic variables, because they really are used to represent many logical decisions. So if we see it y equals 1, it means the binary variable is true. So it means we select this, or yes option, we select this option. If this is 0, then this option is false, or we don't select this item. So this is what we have seen in the case study already. But if I want to say some logic operation, if I say at most 1 is true, how do I represent it? Because sometimes I have multiple options. I want to say if I have my reactor 1 selected, I cannot select my reactor 2 or 3. Or here 2 variable, I cannot. So it means if at most 1 is true, how do I represent it? That makes sense. If I only have 2, I start with 2 options. I have y1 or x1, y1, that's right. y1 and y2 are my decision variables. So here I say at most 1 is true, or it means at least 1 false, because I only have 2 options. Right, so this is logic. So because I only have 2, if I just write it, enumerate all the options, I have better solution. I have these two options, right? So I have my 2 options here. So at most 1 is true, means I can have y1 true or y2 true, or both false, right? So these 3 are okay. At most 1 is true, which means I can select 1, or I don't select at all. So if you have this kind of thing, you can model it. You can model your decision using the binary variables. Here you can write y1 multiplied by y2 equals 0, because at least 1 is 0. Or you can use y1 plus y2. Right, this is 1, 1, 0. So this should be smaller or equal than 1. But this option is not allowed because both are true, not at least at most 1. So it must be smaller or equal than 1. So this is modeling way. I think this is more straightforward because whenever we see 1, at least 1 is 0, I want to multiply that, make them 0. But when you solve it, you will see this is very difficult because these are both decision variables, right? You have 0, 1, 0, 1. We'll multiply them. It will be nonlinear, or bilinear in this case too. So this will be very difficult to solve. Although modeling seems the same, but when you solve it, it adds more challenges. Linear is much efficient to be solved. So this is a preferred modeling way, you can just write this x1 plus x2. It's a linear expression. This is one logic decision we have made for 2 decisions. If I have more, if I have yj indicate all my decisions, I have n decisions, what happened? What does this indication mean? So even if you use the linear expression of the binary variables, you can indicate actually a lot different meaning, right? If I have yj, for example, if it's, let's start with the equal. If I see summation of all the yj equals 1, it means I can only select exactly one option. I can only select one vector and the other cannot be selected. So it's only one choice give me return 1, the other all return a value of 0. So when I sum them together, the summation is 1. But if I say all my y summed together is larger or equal than 1, what does this mean? So it can be 1, can be 2, can be 3, but cannot be 0. Right, so it means at least one item should be selected. It must be one choice, cannot all be 0. But if it's yj smaller or equal than 1, also it's straightforward. A summation can either be 1 like this, means select exactly one item, or it can be 0, means select nothing. So it means at most select one item, so no more than one item. So this is a design. How do you describe the decision process? You can use the binary variable to indicate, just make my decision as a variable, binary variable, and then to model your decisions based on the statement you're giving conditions. Is that clear? This is a basic logic variable. And in further, can you try to think about more? So the first one that you might use in your normal math or decision making. But then we have more modeling techniques that's very interesting. You allow abundant modeling techniques you can use to form your optimization problem. So look at this. If we modeling the binary variables, like say 2 yk and yj, if I see yk minus yj is smaller or equal than 0, so this is a common inequality constraint, just minus still linear expression. So what does this mean? So again, because they are binary, the nice thing about binary, we can write all the options. So if yk must be smaller than yj, so it means either smaller or equal. So that means either this, or this. Is that correct? So what does this mean? So it means if I select k, then I must select j. That's correct or not? Oh, good. I might make it wrong. equation, so yk equals yj, it's okay. It means if I select k, then I select j. So it means these two decisions are equivalent, right? If it's an equality, then my yk and yj, although their decision is unknown, they're exactly the same. So it means they are equivalent decisions. If I select k, I must select j. And the same, if I select j, I must select k. So if the choice can only be both true or both wrong, both not true. But the first one, can you explain the first one for me? Is this correct? Correct? What does this mean? I even got confused, so if you could explain the first one. If yk minus yj, if I want to write the decision in this way, what does this mean?
The first one, when yk is 1, then yj needs to be 1 to make the equation true. So if yk is 0, then yj can also be 1. And still satisfy the equation.
So what does this mean then? So I think it speaks very good way of clear logic. You make say, if I have yk minus yj smaller or equal than 0, say if I select my yk, then my yj must be 1. So if my first choice is 1, second choice must be 1. So that means this way is right. If I choose 1, I must choose the other one. But if my first one is 0, then my second one can be anything. So it's always hold. So this way you just constrain one, kind of a relaxed constraint than the second one. It only means if I choose first k, I must go by 1, must get 1. But now if you don't buy 1, then it's free. Just this constraint is relaxed. So this is a way to model the coupling relationship between these two. Instead of saying they are exactly the same option, you must be at the same time choose or not choose. You can make the relaxed constraint here. So it's one way. To try to think in very good logic to think about if you choose first or if you don't choose first, then what does this mean? Right? Okay. And also the second part is also a new thing. We want to model it. You can use a magic number here. It's called big M. So it's quite interesting. So what does this big M mean? It's a huge number. It can be 1 million. Any big number, but it's fixed number. Just you give it a very large number called a big parameter. It's big positive number. Then you can use this big M to model some relationship. Some initial relationship might be different, might be complex, but then you can use the big M to model the different relationship. Take a look at this and try to understand what does this mean. So that you manually introduce this new parameter M. So if I want to express my initial constraint, F1 and F2, I have my constraint to say, oh, it's either F1 smaller or equal than 0 or F2 smaller or equal than 0. So it's some constraint will model you might use. It's either this condition or that condition, but you don't have to have them both holds. But it's difficult to write in constraint. You write R. You have to program in a very difficult way. You have to say, oh, if this holds, then the other does not have to program the logic. The logic is difficult to be programmed in a computer. That's why they use the logic variables, binary variables, 0, 1, plus this big M to make the decision. So I introduce a decision variable, y1 and y2, so they are binary variables. I make them. And then we just talk about if the summation of the binary variables are 1, it means what? It means choose exactly one option, because it can only one be true, the other be wrong. So, but it cannot be both true or both wrong. So it means choose exactly one. And then why do I need these constraints? It really means when I choose 1, if y1 is 1, so if I choose I must choose 1. So if I choose y1, then this 1 minus y1 becomes what? Becomes 0, right? So this big M will be no functioning because any number multiplied by 0 is 0. So it means 1x is smaller or equal than 0 if I choose my y1 equals 1. So this means if I choose y1, then this constraint holds. But if I choose my y1, how about the second condition? y1 is 1, but y2, then it's 0, right? So this second one naturally become 1 minus 0 is 1. So it means f2 smaller or equal than m. So why do I add this? Because m is the big number, right? If you pick sufficiently big, this will not constrain it because your feasible region is here, but you pick m here. So either it's smaller than m, it won't be an active bounding constraint at all. So it's just like you add a redundant constraint. But in this way, you don't have to make this judgment. You don't have to say I choose 1 or 2 or I got a constraint. You just use this formulation to introduce the 2 logical variables and then use this big M to clear your constraints. So this is a very commonly useful one because sometimes when you directly formulate your program, it will be very slow to do a loud judgment in your constraints. But then if you introduce your some big M number or some similar way, you can use a negative number in different ways, it will bring a lot of convenience in computing. So I really like the magic part of this big M, and you can think about some other examples. But here it also gives you another example. Some logic relationship. If you say if my y is 1, if y is chosen, then my constraint h is 0. Then you can write the relationship in y multiplied by hx equals 0. Right? Because when your y is 1, you got this. But this again is multiplying relationship. It has some nonlinearity here. I don't prefer to use this way. So I can again use a constraint. Instead of saying hx equals 0, I introduce my hx with 2 boundaries. So the lower limit is minus m multiplied by 1 minus y. And the upper boundary is m multiplied by 1 minus y. So what does this mean? So you don't directly use y, you use 1 minus y. Right, so this means if your decision variable is 1, if you choose this y, this term becomes 0. So 1 minus y is 0, then this side is 0, this side is 0. Directly, hx is 0. This constraint is active. So let's miss my goal. But if I don't choose y1, if y equals 0, then y equals 0, this lower bound will be minus m, upper bound will be m. But your m is a huge number, as we say. It won't be constrain the problem at all. So in this case, it's kind of like non-existing, it's redundant constraint. So it forms this way. But if you say this, you just introduce this is a number, so it won't cause any numeric difficulty, just multiply a number. But this is decision variable binary. So this is still linear because it's just one number multiplied by a decision variable. This is also linear. So instead of this directly multiplying a constraint with a variable, you use this big M to turn the constraint in a linear relationship. Right, so this is the case that I'm giving here. Because here I say if y equals 1, then hx equals 0. If I say if y equals 0, if I don't choose y, then hx equals 0. You can think about how to write the constraint. Okay? But this is a modeling way. So this will be very commonly used when you design some problem or you model some correlations among different systems. They will be interacting. Or if you have decided some market strategies, it's only one set of price work. So you have different options, but then you need to model the different options about their relationship. So this is the modeling technique here. Okay. So is this clear? Or if you find it confusing, try to think through it and write down some of the. You can use my way, enumerate it, and then you can compare with it with the final solution. But when you face your real problem, you can think about the modeling. Right. So this is the more advanced one. So now instead of just giving a logic, I want to restrict my range of values. So I can use the, so this means that in this problem, I want to introduce a series of binary variables y. To use this y to give my range of x. So if my x is not just binary, but they can only be A1, A2, they can only be 10, 20, or 30. You no longer use the binary variables to indicate it, but you can use another set of binary variables and then use the different weights multiplied by the binary variables. This way you will be able to describe the discrete range of x. So this is also some special case when you want to describe the x, but if you directly say x can only be these values, it may be not that effective, but using binary variables is more computing fast. Right, so this case, it means if I can only choose x from A1 to AM, then this means I exactly choose one y. Right, so it means only one among 1 to m holds. So whichever j here I choose, I will get a corresponding value for x. Of course, it can have different way, but in this case, I refine my x variable within this range. Right. Also, this is even more advanced. When I have this is discrete value. This is discrete functions. So instead of combining some values, sometimes my functions are combined as well. So I can use my binary variables y to multiply by different functions and then do the functional combination. I think this may not be used in the current level, but it's very useful when you have like market price or some, like you have your C function, for example, is either 0 or is either this linear. Right? So if you just write in this way, it's not a continuous function because it's at this point 0 is 0, but when it's larger than 0, it's a linear function. So you can write in this way, but it won't be a continuous problem for a computer to solve. The optimization will give you some infeasibility because it's not continuous. If you want to model this better, we can then use the y binary variables. So look at this to see x is smaller or equal than uy. Well, this objective function, instead of k plus c, not objective, sorry, this is a model of the function. Instead of k plus cx for the linear, it's multiplying this k this k is a constant, right? A linear constant multiplied by y. So what does this mean then? So it means when your binary y is 0, this country will become x is smaller or equal than 0, because x is non-negative, so it's only x equals 0. So when your y is 0, then this function directly has a value of 0. If you will make the binary to make y equal 0, then this x must be 0, then this function value is 0, so it indicates this value. But if your y is not 0, it's 1, then your function will be k plus c x directly, because your y is 1, and your x is smaller or equal than u. So here, if it's an upper bound for u, you can have that. If it's no upper bound, you can again use a big M strategy. So this is the way we indicate the discontinuous function using the binary variables. So once it's uniform, it's easier to be solved using the mixed integer programming. So all we discuss here is modeling techniques. What it can do is when you model a problem, you make it easier to solve. If you have a simple machine, of course, you don't mind the simplifying model. You can just make any difficult model and throw it to the computer to solve for 10 days. But just think about your compute. Computer is good, but it's not almighty. It can cause a lot of trouble because people stop to think. Just use a very, sometimes not that smart model. You can do some modifications in the modeling stage, and the computing will be much more efficient. So that's the whole thing why we need the modeling techniques here. Okay, so lastly, I think it's just a let me see, example about the facility location, because this is relevant to the group project as well. So this is also a typical type of optimization. I think some of you have chosen to do this in the individual project, right? But this is a typical, like if you think about it, it's kind of a network example. If you have potential facility locations, let's say n locations, and if you have m clients that you need to serve from these locations, and then you have the fixed cost, right? So you got your map here. You have all your clients, all the people to serve, like your market is distributed. So it's like the project I give you, like if you have your marketplace for your fertilizer, for example, is distributed around. How do you send the production center to meet those end users? Because you cannot build. Now we have a lot of modularized products. So by the way, it's okay. Whenever there is a user, I have a plant. Like I run a portable plant. That's kind of extreme. Or I can have a center plant as a center to serve all, like a super large plant. So that's kind of too extreme. But in optimization, we can always form some optimization problem to find the most economic optimal solution. So you got some cost value. You know the fixed cost is to operate a facility and location. So here to use the location well, at location G, you have fixed cost CG. Well, you have the distance cost, like the transportation cost. We call it Dij. Means if we serve a client I from a facility J. Then we need to select the site of facility locations and send each client to one facility while minimizing the total cost. So this is the type of optimization you can solve to get your group project done. Because it's a lot of aspects in the urban design, right? It's like an urban system, urban resource system. You need to fulfill people's demand using some service. But where to construct your service is a good point. But in the group project, I hope you can model it more interestingly. You can either use some real location information or try to use some skills. Like last year, some students used some clustering technologies, like the clustering algorithm to do some cluster first and then serve the demand by each cluster. So that's also a possible algorithm you can be creative to make. But by simplification, it's like you have the demand clusters and find the server center to solve it. So if we just a basic level optimization, then we can write down all the options here, right? We have n facility locations, m clients, fixed cost, operating cost. Then my goal is to minimize the total fixed cost and operating cost. But my fixed cost is relevant to how many facilities I open, while my distance cost is relevant to where I transport from locations. So you should pay attention to those locations. You sum over all the facilities or sum over all the distance. Well, it has some more constraints. You can say I can only construct one facility, or if I can have only certain different limit there. So this is the algorithm we introduced. Like if we say x is a decision variable of the travel distance, then what does this mean? Think about those constraints. If xij is 1, it means this client I is served by facility j. So it means this, if we sum xij together equals 1, it means exactly one facility serves this client. It cannot be larger than 1, cannot be 2, but just 1. It cannot be 0, it must be served, but only served by 1. But this is not necessarily true in real world. So when you model your own problem, you should think which constraint you should add. So like modeling works like you state your assumption and then you base on your assumption to make the models. But integers are very useful in making such models. Okay. And again, we say yj is decision whether we open or not. So your xij, it means serving from the j facility, it must be smaller or equal than yj. If I don't open a facility at all, my xij cannot be operating because there's no facility at all for yj. Alright, so this is the basic side. I can use the decisions. Like you can also use some, if you have more facilities serving one client, you don't have to make it an integer or binary variable. You can use this as a fraction. The part of it can be served by this facility, or the other part can be served, but summation equals 1. So that's all the possibilities of modeling. Right, so I also provide a GAMS code for this one. Actually, this has more advanced examples than this, but this part just give you a sense. Similar idea, you have regions, you have warehouse, you want to, so that is not exactly the same. You can have a look of this. I think this is also like a warehouse problem, but it's different. You can try to understand how it's modeled in a way. Just want to show you, if you want to express, because the cost is very location dependent. So the transportation cost, if you want to write it down, it can be in this way. But many of you have already used some smart way to read the data between different software, right? You don't have to copy all the number here in the old-fashioned way. You can directly read from your data site or using a program. Okay? So this can be a reference code for project already. So this is kind of base level. If you do the project at the same difficulty level as this, it's oversimplified. So hope you can, for group projects, individual has submitted already, so it's no problem. For group project, at least you should consider some more exciting problem, right? Okay. This is a quick summary. So we say the MIT is solvable, right? So we can solve exactly the mixed integer linear programming. Some algorithms I introduce the cutting planes to you, and some of those cutting planes methods are introduced. And you can also use some heuristic methods. I think from next week we should start to learn some heuristic methods. That is kind of the genetic programming. You heard those called swarm optimization, right? So it seems more exciting, but actually they are more simpler because for the traditional algorithm, you have to understand the reasoning. For heuristic, it's based on some magic techniques. They say I follow the people's behavior, I follow the swarm behavior, and then I got to heuristically find some optimal solution. But it's a lot of ways to solve those optimal optimization problems. And you just know those different terms. And if you just want to use software, simplex, and it's the most powerful one to serve integer programming now. So most time it gives the best performance for simplex. If you get someone base set performance, of course it's not good for MI-NLP. So if you are interested, try to develop something for MI-NLP, that will be very powerful. Okay, and this is a more advanced example to show you how to do a portfolio optimization for MI-NLP. This is actually from the GAMS library, so we won't touch the details now, but I just also has integer variable. If you're interested, you can have a look. It's good for your investment plan to do a portfolio optimization. So that's more financial relevant. Right, so I think that's a mixed integer programming part we have finished. But just quickly, next week, we will, because we finished this already, so we start to introduce some more general heuristic and stochastic, multi-objective, and then we can briefly teach some machine learning, and we have discussion on group project as well. So hope next week you can probably start to work with your group already to spend some time in class to discuss with your group members and also with me, because it's the valuable time we can then fix the plan. You can start to fix the scope. Don't overthink about what you do. Just start to do some interesting examples as early as possible, and then let's do a quiz and do more review later. Okay, thank you.
And computer science.